Video 56 of the master course Corner Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is van der Waals coefficients. In the beginning of chapter 4, when we were expanding the electrostatic potential coming from the charges in a molecule in the moment series, we were discussing that these moments are important for describing the interaction between molecules, so the intermolecular interactions, where we would have interactions between moments, dipole moments of molecules and quadrupole moments, and so forth. Now that is the purely electrostatic interaction. In this chapter, we want to come back to this topic and look at the dispersion forces or London forces, meaning looking at the dispersion energy and try to see what the quantum mechanical expression for this is. And we will find out that they are actually related to the frequency-dependent polarizabilities of the two molecules which interact. And this makes a lot of sense, or is in agreement with the more classical interpretation of the dispersion interaction as being the interaction between induced dipole moments. And as we have seen in chapter 4, the first contribution to the induced dipole moment comes from the polarizability. The derivation of the expression for the dispersion energy, that will just be simply based on perturbation theory. And the perturbation Hamiltonian is then the interaction, the operator describing the interaction between two molecules, which means it's the interaction between the two charge distributions of the two molecules. And one expands then those charge distributions in the way we've done it in the beginning of chapter 4 in the moment series, and then keeps the first term. And the first term is then going to be, for uncharged molecules, the first term is then going to be the interaction between the dipoles of the two systems. So it's the dipole-dipole interaction term. And we have in previous chapters seen terms like this, which are then here the dipole-dipole interaction term. And it depends to the third power of the distance between the two charge distributions. And here we have the dipole moment operator for one of the two molecules, and here we have the dipole moment operator for the other two molecules. And as I said, the molecules are separated by a distance RAB. Now the unperturbed Hamiltonian for that system, well, the unperturbed Hamiltonian for the system, which is a complex of two molecules A and B, then it's just the sum of the Hamiltonians of the two molecules which are not interacting. So it's just the sum of the normal unperturbed Hamiltonian for one molecule, molecule A, plus the corresponding Hamiltonian for molecule B, which also means that the zeroth order energy, the unperturbed energy of the complex is then just the sum of the two unperturbed energies. And similarly, we write the complex wave function, the unperturbed complex wave function, then just as the product of the two unperturbed wave function of the two separated systems. So perturbation theory, so we get a first order correction, and the first correction perturbation theory is like always, it's the expectation value of the first order Hamiltonian with the zeroth order wave function, which means it's just the product of the two unperturbed wave functions and our first order Hamiltonian. Now the first order Hamiltonian, remember from the page before, it's products, scalar products of the dipole moment operators for the two molecules. And since the wave function here is a product of the unperturbed wave functions, of course the dipole moment operator of molecule A is only going to act on the wave function of molecule A and vice versa for B, which means that the first order energy correction then just is an expression like this here, where we have then the dipole moment of molecule A and the dipole moment of molecule B. So it's basically just the expectation value of the perturbation operator. The second order energy correction is then the usual sum of states expression, where we here have the first order operator. We have again the zeroth order wave functions here in the ground state and the excited state, where the excited state here means that either molecule A or molecule B is in the excited state, or both of them. So it's basically all the other states except the one where both are in the ground state And these are then the zeroth order energies, which is just the sum of the corresponding energies of the two separated molecules. Now we can now distinguish between two different cases. We can distinguish the case where one of the molecules is in the ground state in both situations. So here we have both in the ground state, but in the excited state here in our summation, we can choose the situation where molecule B is still in the ground state, so it's excited because molecule A is in excited state. And of course, vice versa, you could look at the corresponding term where molecule A would be all the time in the ground state and only molecule B is excited. This contribution to the interaction energy is called the induction energy to the intermolecular forces or the intermolecular energy. And if you set the operator in, you can show that it's actually, in this case here, we have the excited state for molecule A. It's going to be a term which involves the static polarizability of molecule A and the permanent electric dipole moment of molecule B. And we're not going to look at that further because this is the induction energy. So what remains from the second order term is then the terms where both molecules are in the excited state. Here, both molecules are in the excited state. So I have a sum over all the excited states for molecule A and a sum over all the excited states for molecule B. Now inserting our product, our unperturbed product wave functions, which are of course also product wave functions for the excited states, we get this expression, and similar inserting the expression for the zeroth order energy, which is just the sum of the corresponding energies, unperturbed energies of the two systems A and B. We can write this term in this form here, where I have here an energy difference between ground and excited state for molecule A, plus an energy difference between ground and excited state for molecule B here. And in the numerator, I have a usual kind of a transition moment with here our perturbation operator. Let's look at that more. And right here is the norm squared. Remember what the expression for the first order operator, which involves the dipole moment operator of both systems, we can actually write it in this way here, where we have here a scalar product of transition moments with the dipole moment operator of molecule A and ground excited states of molecule A and correspondingly for molecule B. And here it's written in a more tensor notation. Now, this is the correct expression where we will take care of all kind of orientations of the molecules, but in the gas phase or the liquid phase, both molecules, of course, have the possibility to rotate. And for this, to describe this situation, we have to take an average of these possible arrangements, which gives us the isotropic interaction. And then the transition moment can be written in this form here, where we have just separate the transition moment for molecule A squared times the transition moment for molecule B squared, and now divided by the distance between the two molecules to the 6th power. In detail, which means our expression for the dispersion energy looks like this. So it's 1 over the distance between them to the 6th power, and then we have here a double sum over the excited states of molecule A and the excited states of molecule B. And we have the transition strength, so the absolute square of the transition moment for molecule A and for molecule B divided by, in a way, divided by the excitation energies for molecule A and excitation energies for molecule B. Now, of course, if I want to calculate the dispersion energy, one could do it like this. Which would require to calculate all the excited states of molecule A in order to calculate transition moments and the excitation energies, and similar for B, which of course we could get those from finding the transition moments and the excitation energies from the corresponding response function for molecule A and for molecule B. But in order to get a better physical understanding, let's do a trick. Let's try to separate this denominator here, which is sort of a sum of two terms. Let's try to separate it and sum of two terms, and one depends on molecule A and the other one depends on molecule B. Let's try to separate it in the product of terms where only one depends on A and the other one depends on B. And for this one can use this integral transform, which is precisely splitting up 1 over x plus y into an integral over, but an integral over a product which only depends on x and this new variable z, and times a term which only depends on y and this new variable z here. So this way we have now separate x and y. Here was 1 over plus in a product of two terms where each one only depends on one. So if you apply the same trick to this denominator up here, then we can rewrite the dispersion energy in this way here. So that's all the same, but now we have the integral over this new, not yet defined variable z. And we have still a summation over all the states for A, but now we have here a ratio which only involves system A, and we have a correspondingly ratio here which only involves system B. Now if we identify or choose to identify this variable z as to be I mean the imaginary I square root of minus 1 times h bar omega, which means it's a frequency, or it's the energy of a frequency, but it's an imaginary frequency. If we identify it in this way, then we can see that this term here, the first term, that is actually the frequency-dependent polarizability of system A, but for imaginary frequencies. Because remember, if there would be a minus sign here, then it would be just the frequency-dependent polarizability, but because it's a plus, it's not for real frequencies, but it's for purely imaginary frequencies corresponding. This is then the frequency-dependent polarizability of system B, again for an imaginary frequency. So we can write here the dispersion energy as essentially 1 over the distance to the 6th power between the two systems, and then an integral over all frequency, or all imaginary frequencies, over the product of the two frequency-dependent polarizabilities. And the natural constants and this integral, that is called the so-called van der Waals or C6 coefficient. Yeah. And it's defined this way. So that's the van der Waals dispersion coefficient, the so-called C6 van der Waals dispersion coefficient, and it's called 6 because it goes with the intermolecular distance to the 6th power. And this is this expression here is called the Qcmep polar formula. As I said, this is for isotropic interactions, which of course is immediately applicable to the interaction of atoms, and it's for the interaction of molecules if one assumes that they can freely rotate. One can derive similar but more complicated expressions for the situation where the orientation of the two molecules is fixed, so you don't have that freely rotating. Now, the polarizabilities for imaginary frequencies, well, that's just the linear response function, the usual linear response function, with the only difference that now you have to calculate it for imaginary frequencies. And with some programs you actually can do that. The Dalton program actually can do that. Otherwise, one can use a different trick. So if you don't have a program which can calculate frequency-dependent polarizability for imaginary frequencies, then you can use the Cauchy expansion, the expansion in Cauchy moments, which we just had in the lecture before of the frequency-dependent polarizabilities. So you have to calculate the S-sum rules, S minus 2, which is the static polarizability, S minus 4, S minus 6, and so forth, and then insert them in this expansion and just evaluate this expansion then for imaginary frequencies. Now, when we discussed this in the last lecture, I stated that this expansion is only valid for frequencies which are below the first excitation energy, which of course is going to be a problem then, But one can attack this problem by using what is called analytical continuation techniques based on Pade approximants. One can use that for continuing this expansion to the also in the complex plane, as we have to do here because we need it for imaginary frequencies. And in particular, there are two Pade approximants to the polarizability which can be used here, and one can show that they form a lower bound and an upper bound for the frequency-dependent polarizability for imaginary frequencies. And this way, so if one can evaluate these Pade approximants, then one gets a lower and upper bound for them. But these two are two different types of Pade approximants. Alternatively, one can use the same type of Pade approximant, but as for the lower bound, but now applied not to the frequency-dependent polarizability for over imaginary frequencies, but to the difference between the Thomas-Raiche-Kuhn sum rule and the frequency squared times the imaginary the polarizability over imaginary frequencies, which one then typically calls in this form with beta here, and therefore one can also get an upper bound to the frequency-dependent polarizabilities over imaginary frequencies from the same kind of Pade approximant. And then if one has a lower and upper bound, then one can sort of approximate the polarizability in this way.